Jonathan is an independent researcher, author, lecturer, and entrepreneur who is one of the leading international experts on the economics of climate solutions and the energy and environmental effects of information technology. He's perhaps also best known for Koomey's law, an iteration of which I would have had in my intro presentation. So unfortunately, you didn't get to see my version, but I'm sure Jonathan is going to talk more about that. He has written extensively about data center energy efficiency and has been quoted widely, including in the New York Times, Wall Street Journal, and the Washington Post, among many others. And today he is here to tell us what's next for computing performance and energy efficiency. John, thanks for being here, and please take it away.
Thanks so much for that gracious introduction. I'm going to bring some data to bear on these questions of trends in efficiency and performance, because I think they will help us understand better the challenges and the deep uncertainties that face us when we're trying to figure out just how much power information technology and AI in particular will be using. All right, so I'm going to quick go through some history here. Most of you know this, the energy efficiency of general purpose computing devices at peak output has improved rapidly historically, but things have slowed down in recent years. It's a very specific statement, okay? I'm talking about general purpose computers, which is what most people focus on when they talk about these long-term trends. We mean CPUs, basically. And I'm also looking specifically at the efficiency at peak output when the device is running flat out. This is in the old days, it didn't matter so much because the power used was pretty much constant. But nowadays, as we've gotten more clever at reducing power use, making things more energy proportional, the total typical use efficiency is a very different thing than at peak output. But we have the data for peak output going back a long ways, and so that's traditionally what we've focused on. So this is the graph of that for computing systems over time. Before the year 2000, when Dennard scaling ended, the efficiency of peak output basically doubled every 1.6 years for these systems. And you see that going back all the way to ENIAC. You see that trend for the vacuum tube computers. There's a big jump around 1960 as we switched to discrete transistors. And then the shift to microprocessors continues the trend onward. This is from some work in the Annals of the History of Computing that we did back in 2011. So in 2016, Sam Nafziger and I, Sam's at AMD, we looked at some of their internal data, which they were happy to share with the world. And they showed that things had slowed after the year 2000. And actually, when we went back and looked at those earlier data that we had used and took some of the data from 2000 to 2009, those data also showed a slowing. But at the time, I didn't think to do that regression. So in any case, the doubling time slowed to a doubling every 2.6 years. So that's still improving pretty fast compared to many kinds of technology, but it's much slower than it was historically. Now, there have been other examples of improvements over time, and you end up with similar numbers for network electricity intensity per gigabyte, where we saw about halving every 2 years after 2000 for broadband downloads. This is from some work that I did with Sony PlayStation, and so similar kinds of trends, basically efficiency doubling every 2 years. There's also work on the total electricity use for data centers as a whole. Most of you have probably seen this. It's from our article in Science. It showed from 2010 to 2018 that there are massive increases in the services being delivered, computing services being delivered. So installed storage capacity up 26-fold, data center traffic up 11-fold, data center workloads and compute instances up 6.5-fold, installed base of servers up by about 30%. But all electricity use for all data centers rose just 6% in the time it took for those compute instances to jump 550%. So really substantial increases in the service demand that were offset almost entirely by improvements in efficiency. And so that's the big story of information technology over time. Compute demand always seems to go up very rapidly, but people also forget that at the same time, efficiency also goes up. And sometimes it completely or almost completely offsets the service demand in terms of energy use. Sometimes it doesn't quite. So from 2000 to 2005, we had a doubling of electricity use for data centers. But it's never true, virtually never true, that the service demand goes up and there's no improvement in efficiency. And unfortunately, a lot of people still forget that when they make these kind of wild projections of where we're going in terms of computing electricity use. So data use, data transfers, computation, growth in those things, this doesn't necessarily imply growth in computing electricity use. It can, but it need not, because this is a sophisticated crowd. I'll put up some equations. So total energy use per year is a function of computations per year times the kilowatt hour per computation, or equivalently computations per year over computations per kilowatt hour. If computations per year goes up faster than computations per kilowatt hour, then total kilowatt hour goes up. But you have to remember that computations per kilowatt hour almost always is improving over time. And that's something that we can say something about, not only how fast that efficiency improves, but also what are the source of those efficiency improvements. Now, in the past, at least for the microprocessor era, the improvements in performance and efficiency came from shrinking transistors, mostly. And that's what, when people talk about Moore's law, they're talking about projection in the density of transistors over time. That's how Moore talked about it. And we all know that that's been slowing for many good reasons. As you shrink transistors more and more, leakage current becomes more and more of an issue. Around 2000, I mentioned that Dennard scaling ended. That's when we ran out of space to reduce voltage as we increased clock speed of chips. But that's not the only potential source of efficiency improvements. And in the past, I think we kind of grew reliant on that progress, but we've ignored some of the other sources of potential efficiency improvements. There's this terrific article in Science by Lyserson from 2020, and it talks about, yes, there's hardware improvements related to die shrink and transistors, but there's also improvements in software. So getting rid of bloatware and being more clever about how we design things, software, hardware co-design. There's also improvements in algorithms that can have a huge impact. And then there's improvements in hardware architecture. So after Dennard scaling ended, there was a shift towards multiple cores on computer chips. That's an example of hardware architecture, but there are many, many more. So we're also seeing a shift from focus on general purpose computing devices towards special purpose devices that are optimized. And so TPUs are a great example. There's a lot of other examples of this type. So it's important to understand that these general trends, when you talk about the slowing of Moore's law, yes, the rate of improvement of transistor density has definitely been slowing for many reasons. But now we're going to have to focus more on some of these other tools for improving efficiency and performance. And just because the density of transistors is slowing down, the improvement in density of transistors is slowing down, doesn't mean that we can't focus on some of these other areas. The problem, of course, is that we have to change some of our institutions, our incentives, our processes to be able to do better at capturing efficiency and performance from these other methods. And so that's something that as an industry we have to face squarely, because it's not going to do to rely on the historical improvements in the density of transistors. Now, one other thing I wanted to bring up that has come up a little bit in the earlier talks, data centers use about 1% of the world's electricity. The networks, access networks, core network, use a little more than 1%. And then all the end user devices use 2%. So those are numbers from Malmedin et al., which is for 2020, pretty typical. So all ICT is about 4% of the world's electricity use. But I like to say that ICT is great at improving efficiency in many different ways. And yes, we use a few percent of the world's electricity for ICT, but it's going to help us make the rest of the electricity and all the fuels a lot more efficient. Bunch of examples here, not really the topic of this talk, but it's important to keep in mind that there's a broader picture. When you think about sustainability, it's not just about direct electricity use. If it's doing good stuff, we might as well use the electricity if it's valuable to society. So we've got to think more whole system when we're thinking about this stuff. So let me just summarize, because it's a quick talk here. We know that these Moore's Law improvements slowed after 2000 because of the end of Dennard scaling mainly, but there's still a lot of room for improvements. And some of the examples of things we can do involve those areas that come from the Lyserson science article, focusing on special purpose computers optimized for specific workloads can free us for a time from these physical limits. Focusing more on system on a chip, putting more and more stuff onto the chip, stacking the silicon, better software design and eliminating software bloat, software-defined infrastructure, better algorithms, co-design of software and hardware, low power modes especially for mobile devices, distributed ultra-low power systems, approximate computing. There's all sorts of other possibilities. We've begun an analysis of the last 50 years of trends in microprocessors, which is uncovering some interesting results, and we expect to have a publication this year on that. But one of the things I learned from doing that work as I looked at those trends for microprocessors as distinct from the system trends from the earlier work is that there's two components of improvement. There's taking an existing processor and shrinking it to make it more efficient. And then there's also incorporating more and more ancillary circuitry onto the chip. So over time, the power use of individual microprocessors has been going up, but they're shrinking so much ancillary circuitry and making it so much more efficient that there's a faster improvement in the systems much faster improvement in the systems than there is in the individual CPUs. So another thing that people need to understand is that even if progress stopped tomorrow, if Moore's Law just stopped dead, all progress in transistor shrinkage stopped, we'd still have 10 to 20 years of fully utilizing our current IT to its potential and applying current process technologies to embedded systems. And those typically lag the best-in-class chips. In that scenario also, there's other ways that we can improve efficiency, and that's what we need to focus on. So I think it's probably true that the biggest effect of data centers are likely to be on the other 99% of the electricity and all the fuels, but that's something that will require a lot more case studies to demonstrate. And I'm pretty sure, based on some of the work that we've done over time, is that in the next few decades, we're going to have to radically change how we do computing if we want rapid efficiency and performance improvements to continue. There's a lot of possibilities for that. People talk about quantum computing. That's a special purpose device for certain kinds of applications. People at Purdue have even demonstrated a single atom transistor, which is kind of an extreme prototype at liquid helium temperatures, but it offers the possibility of very significant improvements beyond what we now do. So this is, I don't like to predict energy use and efficiency far off into the future for ICT. I think it's a fool's errand generally, but it is useful sometimes to do a thought experiment. And back in 2013, we extrapolated that doubling every 1.6 years to see how long it would take to hit the theoretical limit for efficiency that Richard Feynman estimated, I think it was back in '85 was when the book was published. And it looked like in the early 2040s, we were going to run up against that. Now, he looked at a 3-atom transistor and as I said, some academics have demonstrated a one atom transistor, which of course would be much more efficient if we could scale it and make it work. But in any case, I'm pretty sure we're going to have to change what we're doing at some point in the next few decades. But until then, we're going to have to rely on changes in hardware architecture, on software improvements, on algorithms, as well as continuing to shrink things when we can and when it's economic to do so. So the talk itself, I assume, will be posted. If not, I will post it. But I've got a bunch of references in here related to what I talked about. And with that, I will happily take some questions.
Thank you, John. And it looks like we already have a hand up. David, please go right ahead.
Hey, John. Great and super interesting. The comment you made, and this is actually always on my mind, right? It's that kind of consumption standpoint and the actual use patterns by people using all this great, fantastic hardware and capability. I think we're kind of getting to a point where we've got a whole bunch of Lamborghinis and people are still driving them at 20 miles an hour in traffic. And so you were spot on, and I agree. There's a lot of things we're all trying to do in that space. Are there any good, like in your references or somewhere else, are there any good kind of papers or studies on kind of how the performance of the hardware is kind of comparing to the use, the IT software pattern?
So you're talking about utilization? Is that kind of
yeah, effectively talking about utilization, right? We're getting denser, faster and faster cores, but for the most part, everybody just needs a Camry. Not everybody, but like when you think about like enterprise IT, particularly as it relates to cloud and elements like that.
Yeah, so one of the things that happened in that 2010 to 2018 period was this massive shift to hyperscale. And one of the great advantages of hyperscale, as everyone here knows, is that the utilization is much, much higher. So basically, you had a whole bunch of corporate data centers running at a few percent utilization. People were shifting their workloads into the cloud where they were running at 30 to 50% utilization. So that's a factor of 10 improvement in energy and cost per compute right there, to first order. And so that's, I think, the anecdote that I remember is that shift from corporate data centers, the server huggers, to the hyperscale facilities. That is the big jump. Now, eventually, you run out of that, right? You run out of
and that's what
really
I'm seeing.
low utilization devices.
That definitely happened, right? And that's definitely been good, right?
Yeah.
But I'm curious about the curve of how enterprise workloads are changing, right? Because if it's just going to still be a bunch of forever lift and shift, right? The processors on these machines are going to get better and better and better and better, and their capabilities are going to get better and better. And we're going to have software that dense packs things more and more. But I'm just curious about workload trends, and if it's not.
Well, I think as we get more, I think that's the question for VMware and folks of this type, because they're getting better at moving workloads around. But ultimately, the name of the game is to get as high utilization as you can get without impacting latency, right? You don't want to have utilization be too high, because then you can't respond if there's a big jump in the demand, right? So I think I don't have data on that. I have that kind of historical anecdote about the corporate data centers. I think it's very application specific. And so what I would suggest is, for those who are interested in that, we need case studies like that. We need to be able to show people, look, you're not using this very expensive resource to full potential. So let's identify those opportunities, because again, that's a big area where we can show improvement, right? We can definitely improve performance and efficiency if we're utilizing our hardware better. Because almost always, even now, after all this work we've done, we're not perfectly energy proportional. So the more you can spread that fixed energy use for having the devices over more service, the cheaper that service is per energy use or per, whatever. So I think that's really, to me, the name of the game right now is case studies showing that kind of inefficiency that can highlight the issue for people, because there's great potential and we're just not capturing it the way we should.
Agree 100% on those case studies needed. Thanks.
One more question for John while I set up my screen share. If not, thanks, John.